All right, this is same worksheet. This is problem number 2. We have a 70-kilogram woman and her son, 35 kilogram. They're standing at rest on an ice on an ice rink as shown. They push against each other for some time of 0.6 seconds. Okay, causing them to glide apart. The speed of the woman immediately after they separate is 0.55 meters per second. Assume during their push, friction is negligible compared with the forces the people exert on each other. So I want you to think about forces for just a minute. So here's the sun. We're going to call this person A and this person B. So this is the force of A that's acting on B. And we'll just ignore gravity and force normal for just a second. And then, as you know, because of Newton's third law, the force that the mother feels is identical to the force that the son feels, just in the opposite direction. Okay. So we know that those forces are equal in magnitude, opposite in direction. That's the first question is calculate the magnitude of the impulse exerted on the son by the mother. Okay. So I want impulse of B equals question mark. Okay, so I want to know how much the change in momentum. So this is force of A on B times the change in time, or that will also equal the change in momentum of B. Okay, force on the son, impulse exerted on the son by the mother. So I don't know the force. I know the time. And I don't know the change in momentum of the boy. But what I do know is what happened to the mother. Impulse on the mom, which is equal to the force that was acted on the mom by the son, which we called object A, change in time, which will equal its change in momentum. Okay, oops, wrong subscript. Okay. Now, so I can calculate that. I can calculate the change in momentum of the mother, right? So we're going to find the change in momentum of the mother, which is momentum final minus momentum initial, and that will equal her velocity final times her mass minus her velocity initial times her mass. Okay. Now, her initial velocity is 0. Her velocity final is negative 0.55. So we have 0.55 times her mass, and that will equal a negative, this is a negative number, negative 38.5 kilogram meter per second. Now that is her magnitude and direction of her change in momentum, okay? So we now know, if you recall, when we derived our conservation of momentum, when we used our Newton's third law to derive conservation of momentum, we know that the change in momentum of A, the negative change in momentum of A, is equal to the change in momentum of B. The change in momentum during a collision of B is exactly the change in momentum of A, just opposite direction, okay? So I know that the change in momentum on the sun is 38.5 kilograms meters per second. Now they only asked for the magnitude, so we didn't really care about the negatives, but I wanted to go through all of it. So there's the answer to that question. Now, calculate the magnitude of the average force acted on the sun, the magnitude, so we don't care about direction, of the average force exerted on the sun by the mother. Exerted on the sun by the mother. So we don't really care about direction. We know that force, change in time, those forces are identical. The change in momentums are identical. So we'll just find the change in force is equal to the change in momentum over change in time. And we get 38.5 divided by 0.6 seconds. And we get that to be 64.2 newtons. Calculate the initial speed of the sun after the push. Well, if we know that the change in momentum of the sun, which we call B, is equal to 38.5 kilograms meters per second, that has to equal momentum final minus momentum initial, which was 0. So we know that has to equal its final velocity of B times the mass of B. And we'll solve now for final velocity of the boy, which would be 38.5 divided by its mass, which was 35 kilograms. And we will find the final velocity of this child to be 1.1 meters per second. How do the all right, D again, how do the magnitude and the direction of the average force exerted on the mother by the sun during the push compared to those of the average force exerted on the sun by the mother? So if you go back up here and look at our free body diagram that we did, right, we have already basically reviewed that force. So during the push, the forces between the two of them are equal in magnitude, opposite in direction. And the answer is, and you have to justify that. So let's answer the question. How do the magnitude? So the average force exerted on the mother, the average force exerted on the mother by sun is equal in magnitude and opposite in direction. Because of Newton's third law. Okay. All right. After the initial push, the friction on the ice that the ice exerts cannot be considered negligible, and the mother comes to rest, moving a distance of 0.7 meters across the ice. If the coefficient of friction are the same, how far does the sun move after the push? Okay, so I just want to do a couple things real quick. So this is the mother. So we called her A, and this was the sun, and we have B. Whoops, I want a little bit closer together. This is B. And this is the free body diagram during the push, right? We have force normal, we have force of gravity, and we have force of B on A. And they told us during that push the friction was negligible. And this is force of A on B. And this was for 0.6 seconds. This is during the push. Okay. Now, after the push, the sun is sliding this way, okay, and has some initial velocity. And what was his initial velocity? Well, you found it to be 1.1 meters per second. So that was immediately after the push, immediately after this explosion, because this is just the opposite of a perfectly inelastic collision. The sun's velocity is 1.1 meters per second. And then the sun will come to what? A velocity of 0, okay? And then the mother had an initial velocity of 0.55 meters per second immediately after the push, and eventually has a velocity of 0. And they told us this delta X was 7 meters, okay? And what is the free body diagram during this time frame? Force normal, force of gravity. It's moving to the left, but it's slowing down because of what? Kinetic friction. This one is moving to the right, but it is slowing down because of kinetic friction to the left. They told us that the coefficient of frictions are the same, so I'm going to probably have to use stuff in the mother's direction to find enough information to solve the son. So if I sum the forces in the x direction on the mom, I find her mass, which is A, we called it, times her acceleration is equal to the force of kinetic friction, which is to the right, so we'll call that positive. Her acceleration is going to be to the right. So look, this is what we have. Her velocity is to the left. Her acceleration has to be to the right. This gentleman is velocity to the right, acceleration to the left, because the net forces are pointing to the left. So we got to find mu. If I know mu, if I know the coefficient of friction, so if I go over here and say sum of the forces in the x direction, mass times acceleration of that child is equal to its coefficient of kinetic friction times, let me not skip a step, the negative force of kinetic friction, which is equal to mu k times Fn. Okay, so I don't know mu k, but I have enough information to find mu k. This is mu k Fn. Because I can find acceleration, right? I have three things. I have her initial velocity of negative 0.55. I know her final velocity is 0. And I know delta x is equal to 7 meters. So I can find acceleration using this equation, v final squared, v initial squared, plus 2a delta x. And if you plug that in, you'll find a equal to 0.0216 meters per second squared. Then you can solve for mu k. Mu k is equal to mass of A times the acceleration of A divided by force normal, which is mass of A divided by G. So if you calculate mu k, let's do it again, ma over ma, and this is the acceleration divided by g. Masses cancel, plug in 0.206 divided by 9.8. You get a really small number for mu k, which is 0.00, I'll call it 22. Okay, so once you have that, you can come over here and solve for acceleration, because we need to know the acceleration of the sun, which is mass times acceleration, which is equal to mu k, this is mass b, times mass b times g. That's what force normal equals. The force of friction is negative, so we have a negative there that I left off. And I can now solve for acceleration, which will be equal to, masses cancel, negative 0.0022 times 9.8. And sure enough, what do we get? We get the exact same acceleration that we had for the mother, 0.0216. Forces were the same. Okay, now that I know that acceleration, that's in meters per second squared, I can find delta x. Delta x is what we're trying to find. So I know its initial velocity, which was 1.1 meters per second. Its final velocity was 0. Acceleration is 0.0216 meters per second squared. I can solve for delta x using 54321. And I will find delta x to be equal to 28 meters. Okay. That is solution for problem number 2.